Hello, welcome back to MATLAB Programming for Engineers. So one class of problems we haven't really had a chance to deal with in the course so far is optimization or parameter estimation, which is a closely related topic. In all the problems we've had so far, we've said, here are the parameters, put those into your calculations and do the calculation. But more of a design-oriented problem in engineering is what should the parameters be to give us best performance? So that's optimization. A related class of problems is parameter estimation, where we have some model that describes how our system should behave, but we don't really know all the values of the parameters that go into the model, but we have some experimental data. So how do we adjust the parameters so that our model produces results that match our experimental data? That's the parameter estimation problem. So I'm going to do an example of that later on, determining the drag coefficient for a skydiver simulation so that it matches some experimental result. Right, but first, let's talk about more of an optimization problem. And this is a very common class of problems in engineering and science, and even in fields like economics and management. How do we choose some set of parameters to maximize or minimize some quantity? And one example of that would be, let's say you're running a business and you want to know how to price your product so that you maximize the profits. Or strictly speaking, the proper term would be net income. Because of course, the higher you price your product, the fewer people will buy it. So do you want to have a low price, but sell a lot of them? Or do you want to have a higher price and sell a smaller number of them? Where's the optimum? So we need some kind of model for that. And what I'm going to assume as a model is a Gaussian function that looks like this, which says the quantity purchased will be a function of the price. And it goes as some constant times e to the minus some other constant, p squared. And of course, I just need to pick some values for those parameters, a and lambda. And the reason I think this is a reasonable model is that it goes to 0 asymptotically as p increases. And so no matter how high you price something, somebody is willing to buy it. Just fewer and fewer people are willing to buy it as you raise the price. So if that's the quantity purchased, well, then what's the total revenue? Well, it's just the price times the quantity purchased. So P times Q of P. And what's the cost of production? Well, we have to think about that too. Production costs will have two components. There will be some fixed costs, like the rent on your factory, management salaries, things like that. And then there are marginal costs, incremental costs, things like direct materials costs. The more product you produce, the more materials you use, so the cost will go up. All right, so B is the fixed costs, and CQ is the variable costs. All right, so now I have to have some numbers, and that, actually determining those numbers would be the hard part. But let's just pick some numbers for A, B, C, and lambda. And just based on these equations, if I take the revenue minus the costs, that would give me the profit. Or if I take the negative of that, then I'll have the opposite of profit, which would be loss. And the reason I'm writing it that way is because MATLAB has built-in functions for minimization. So if what I want to do is maximize the profits, then that means I want to minimize the negative of the profits or minimize the losses. All right, so I have a loss function, which is a function of the price, P, given by the equations that I just showed you. And I want to minimize that. And if I minimize that, that's the same as maximizing the profits. All right, so the built-in function in MATLAB that will do this optimization for you, or at least one of them, there are actually several of them, but the simplest one is called fmin search. where you give it the function you want to minimize, and you give it an initial guess. In this case, the initial guess for P. So let's start by assuming our price is going to be $5, and then let's find the minimum somewhere in that neighborhood. Now, this happens to be a really simple problem, a well-behaved problem. It's not going to matter what we choose for our initial guess. We'll get the same answer anyway. But in more complex problems, it can depend a lot on your initial guess. And so you do have to think about that somewhat. So what this will do, it'll take this function that we're trying to minimize with a starting guess of 5, and it'll find the value of P that minimizes that function. And that's what it will return to me, and I'm calling it optimal price, and then I'm going to print it out. So let's see what happens. All right, it says the optimal price is $8.14, which yields a total profit of $2.2 million. Or again, strictly speaking, it's not profit, it's net income. Now, we could have done this a much simpler way because it's such a simple problem. So just kind of for validation, let's just plot the loss function versus the price. And you see, in fact, it does peak at a price of around $8.14. All right, so that's a simple optimization problem. You have some function and you vary some parameter to minimize that function. Now let's apply it to something that's a little more complex. It doesn't have to be a mathematical function that we have in closed form. It could also be, let's say, a simulation, where the simulation returns that result. And we keep varying that parameter and rerunning the simulation until we minimize or maximize the quantity that we're trying to optimize. So this is an example of parameter estimation, where we have some parachute simulation, skydiver simulation, and we have an experimental result, which was that during the course of the actual event, the skydiver reached a maximum velocity of 377.12 meters per second. And we want to vary the drag coefficient so that it matches that experimental result, right? So that gives us, assuming that all of our other parameters are accurate and the drag coefficient is the one we're uncertain about, we can vary the drag coefficient to match this experimental result, and that gives us an estimate for the drag coefficient. Now we have to think a little bit about what is it we're trying to minimize here. Okay, so we have some simulation function, which is going to run our simulation. We can construct that however we want to return the thing that's most convenient for us. So what I'm going to do, and I'll show it to you here, I'm going to construct my simulation function so that it takes in a certain number of parameters, one of which is the drag coefficient, and returns the maximum velocity, because that's the thing we're trying to match. But that's not what I want to minimize. I don't want to minimize the maximum velocity. I want to minimize the difference. In other words, the absolute value of Vmax minus what the simulation returns. Now, it turns out I constructed this function so that I can just pass it the drag coefficient, and it has default values for all the other parameters. So I'm just going to do that. All right, but keep in mind what I'm doing here. I'm creating an anonymous function. Right? So a function of CD, which is the absolute value of the difference between my, oh, sorry, it's not called vtarget, it's called vtarget, which is the difference between this target velocity and the actual maximum velocity calculated by the simulation. When those two things match, that means I have the right value for the drag coefficient. All right, so how do I get MATLAB to do that for me? fmin search. I give it the function that I want to optimize, which is called error func. And I give it a starting guess. Well, let's just say 1. Okay, so my initial guess for the drag coefficient is 1. Let's see what it gives me. It turns out the actual drag coefficient that produces the correct experimental result is 0.802. Now that's kind of opaque. I just ran this function, it gave me a result. It'd be kind of nice to see what's going on there. Let's go to the simulation function. Let's just put in a disp of CD so we can track it step by step. And so every time fminsearch calls the simulation function, I'll see what value of the drag coefficient it's passing to it. All right, and again, I started at 1. And you see the first thing it did, it tried 1.05. And that produced a worse result, not a better one. So it said, oh, I'm going in the wrong direction. Let me go down instead. So I went to 0.95. That got a little better. That is, in the sense that this error function got smaller. So I said, oh, let me go a little farther in that direction. 0.9, 0.8, 0.7. And then at some point, and I don't know why it did 0.7 twice in a row, but at some point it realized it went too far. It started getting worse again. That is, the error started increasing again. So it went back the other way. It went to 0.85, 0.75. So now you see it's going back and forth because it's got it bracketed. It knows it's between 0.85 and 0.75. So it keeps going back and forth, smaller and smaller differences, until finally it converges to 0.8021. And so this is what's called a simplex method or Nelder-Mead algorithm. And you can look up in a numerical analysis book or on the web if you're interested in knowing more about the theory of how that works. And now the problem that's in the exercise is a little more complex because it actually asks you to optimize 2 parameters. But there are instructions in the exercise that are pretty detailed. It pretty much guides you through the process. But basically what you do is you put the 2 parameters into a vector and you pass that to the anonymous function that you're trying to minimize. Okay. So the argument here would just be something like params, where that params is actually a vector that contains all the parameters we're trying to optimize.